Let's go on to chapter 7 on transcendental functions is the title. And just to give you an idea of what that is, let's look at this. So I've listed a number of transcendental functions. So all the trig functions, sine, cosine, tangent, etc., and their inverses are considered transcendental. Exponential functions as well, log, natural log, any sort of base. Exponentials, e to the x, or even any base to the power of x, 2 to the x. Those are all what are considered transcendental. If you have square roots, like root 2, root 5, fifth root of 18, that kind of thing, those are not considered transcendental. So the word is kind of like it's almost like a not situation, like it isn't this kind, or it just specifies a type of number, type of function, and that's all it is. There's other ways to define it and be real careful about it, but basically it's just talking about all those different types of functions that don't have to do with polynomials. In other words, when you have roots of polynomials like root 2 or fifth root of something, those are all considered not transcendental. So that's what we're talking about. And there's other types as well. But we'll look at later and define hyperbolic functions. Those are also transcendental. So that's what we're talking about in this chapter. Okay, let's go on to 7.1. That is on inverse functions and their derivatives. So first we're going to talk about the definition of an inverse function, definition of a function, and just kind of do some quick review. Well, it's not that quick, but review a lot about functions before we get on to derivatives. And really not going to do much on the actual derivative of inverse functions. We have one theorem, but it's really a kind of a warm up for the next few sections to talk about inverses and things like that. Okay, so let's first look at the definition of a function. So a function, so we want to review all this before we get going on everything else. So a function is a mapping from one set, we'll call it A, so from one set A, it doesn't matter the name of the set, but it's called, well, like the letter, called a domain to another set B called a range such that, and I will abbreviate such that with the backwards symbol like that, for each element of the domain, A, there corresponds exactly one element of the range. That's the key. There corresponds exactly one element of the range B. So I'm sure you've seen that before, should have at least a number of times. So what we have then is suppose we have this picture. Oh, wait, I have stuff down here. Let's go and grab some of these. So let's look at this picture first. We'll just bring these up as needed. I forgot about those. All right, so you have this idea of a mapping from one set to another. So the mapping in this case is just, literally arrows, but a function we are normally, what we're used to defining them with is like f of x squared, x minus 2 root 5, that kind of thing, where you have the mathematical operations. So our mapping in this case we'll have just arrows. We'll say A goes to, say, 1. We'll have B going to 2. And then if you have C going to 2, that's still okay. Because each of these on the left side is mapping to exactly 1. What you can't have going on is it splitting off. You can't have like C going to 3 as well. It's this part right here where you have two different cases, like it goes to here and goes to here. Like, that you can't have. So C cannot correspond to two different things. Okay, so this is not a function, this case here. Okay, so we know I'm not going to put that on there because it's not a function. Okay, and then we're used to looking at graphs and things like that. So you're used to looking at graphing stuff. Say you had something like this. Suppose you had this quadratic, looks like that. Oh, it looks nice, huh? I forgot it does that. Okay, so you have a quadratic. Is that a function? And yeah, of course it is, yeah. So if you have y equal to x squared, is that a function? And it is. Now you have 1 and, say, -1 corresponding to the same thing, but then that's okay. It's okay to have two different things correspond to the same thing. So that would be 1, 1. I know my scale's way off there, but that's okay. So you have 1 corresponding to 1 and -1 corresponding to 1. But you can see if you go backwards, it doesn't work, right? So if you were to flip these arrows around, then that's the problem. Then that is not a function because you have 1 corresponding to two different things, right? So if you have 1 corresponding to -1 and 1, that's not a function. Okay. If you flip it, right? Okay, so we're not going to do that. We want to talk about things that are functions, and then we're going to define the next thing. Our goal is one of the things to look at is inverse functions, so we're looking at inverses. So first define function, which is that. Okay, so next we want to have, what did I have down here? Oh, next is this. And let's go ahead and bring this up. I did this graph already. We can erase this guy. We don't need this. So that's a function, yes. Hopefully we said yes. So it is a function. Let's go ahead and bring up all this, and I'll talk about it as we go. And I kind of apologize for just copying some of this stuff. It's just there's sometimes we get so much stuff. I don't want to spend way too much time copying it out for you. So you can pause and copy and stuff as we go here. I'll try to bring this down so as it go onto the other page, because these are page by page. You could literally like print it out as a PDF and have a page in each pages. Okay, let's talk about this. This is the next important definition of one-to-one. Okay, function f with domain D and range R is one-to-one if f not equal to f of A not equal to f of B, then A does not equal to B. So if these are not equal, then these cannot be equal. Another way of saying that is if it's basically the contrapositive of that. Let me erase this actually. So another way of saying that is not the inverse, but if well, let me talk about this first. Let's go over this. So this is basically saying f of A, if f of A is not, so if these are not the same, which is all of this case, right, then you can't have A and B the same. So in other words, so that's one-to-one. So it's not one-to-one if you have these can be different, and then you have the same function value. Okay, so this case here is not one-to-one. And what you would have learned is the horizontal line test. If you would have learned, that's what you would have looked over. Let me change the color there. So you would have talked about the horizontal line test. And if any horizontal line crosses more than once, then it's not one-to-one. The whole idea is we want to go backwards. We want to flip it and go the other direction. And do you get an inverse function? Or do you get a function, which we will call the inverse function? So I'm describing this as if you do know you've gone through some of this before in algebra. So bear with me on that. Okay, so if we talk about, though, this one is y equals x squared. Okay, that's fine. And so you get this function, but it's not one-to-one. Can we restrict it so that it is a function? Can you remember doing that? So if you have y equal to, let's change back to white here. So if you have y equal to x squared, then if you restrict x to being just positive or non-negative, then you get just this side right here, right? So that is one-to-one. And then you'll be able to find its inverse, which will be that. This is going to be its inverse, which we'll check that out. Oh, this was that the function values are equal, and negative a does not equal a. So that's the problem. So that's the case where you have equality. So we have P and not Q essentially is the case. So that's like the negation of it. So this is true, but this isn't. Okay, so that means not one-to-one. Okay, I had put that was what that meant. So what you would do to solve for this thing is we'll go through this though, but you get x is equal to the plus or minus the square root of y. But x is greater than or equal to 0, so you get you just get the positive case, of course. So y is equal to plus or minus square root of x, but x is positive. And so you get just y is equal to root x. So you get just the top portion. So this is what we're going to call the inverse of x squared for x greater than or equal to 0. And we can see here too that it's one-to-one. Every horizontal line crosses just once, and we're good to go. So let's look at next the definition of inverse. When we do that, that has to do with the composition of functions. Okay, so we talked about one-to-one. That's what we're after here. So this is the definition of one-to-one. So I want you to ponder that. Have some examples in your head. Which ones are which? Not one-to-one? Yes, one-to-one. So I can put that down. So yes, one-to-one. And then this is no, not one-to-one. Okay. So definition of inverse. Here's the next important concept. Definition of inverse. So two functions, f and g, are inverses of each other if and only if f composed with g of x is equal to f of g of x, that's just the definition of composition, equals x, and the other way around, g composed with f of x is equal to g of f of x, which equals x. Okay, so that's what you'll check. We'll look at a couple of those when we do this. All right, so here's a property. So property is that f is 1 to 1. If is equivalent to, or if and only if, f has an inverse. Or is invertible. I.e. that is f inverse exists. So, let me finish up here. So two functions are inverses if and only if that. So if they're inverses, we say, I'll just put down, then we say g equals f inverse, usually. It could be the other way around. Or f equals g inverse. Either way, doesn't really matter the order. Normally we say the first one, first case there. So if they're inverses, that's what you get. You say that the other function is the inverse. So let's talk about finding inverses next. Again, something you've done before. Given a one-to-one function, replace f of x with y, solve for x, or interchange x and y, solve for y, etc. That kind of stuff. So finding inverses. Okay, so another review of that. Okay, so given a one-to-one function, f of x, what you do, so just pretend you're given something, right? So then what you do is you substitute, hopefully this is familiar to you, substitute y for f of x. So replace f of x with y. Let's say it like that. That sounds better, huh? So replace f of x with y. 2, interchange x and y. So you swap them, right? 3, solve for y. And 4, set y equal to f inverse. Technically, you'd have to show their inverses by doing the above process, but we're not going to get too messy in detail like that. So technically, you get down to y equals, then you got to call that function g of x, and then show that this is true, in which case then you may conclude their inverses. But we're not going to do that, don't worry. I don't want to get too detailed when we want to get into integrating functions and inverse functions and all that fun stuff. Okay, so let's look at an example. We'll just give an inverse function. Suppose you have f of x. Do it over here to the side. Let's do it like this, just because I can. We're going to put a little line here. Of course, it's not straight, huh? There we go. All right, so we're going to say f of x is equal to, let me move this over, sorry, is equal to, and this, I picked a more difficult than usual one because just, we're in calc, so let's not just pick something too simple. So x cubed plus 1 to the 5th. Now, you may not know right off the bat, but that has to be 1 to 1. Okay, so we know this must be 1 to 1. Because it's 5th degree, it's an odd power. if you multiply this out, it's still odd. It actually ends up being like a, what, 15th degree or something like that. So it's going to go up on the right and down on the left. So it's odd, and it's 1 to 1. So it basically does that kind of thing. So then, and when you solve it, you do a fifth root. So then the roots are you don't have to worry about the negatives and stuff. So replace f of x with y. So y equal to x cubed plus 1 to the fifth. Now what? Right. That's exactly what you do. You replace them. So x is equal to y cubed plus 1 to the fifth. Replace x with y, or swap them. Now solve for y. Okay, so you do the fifth root on both sides. So it's the fifth root of x equal to y cubed plus 1. So now we're just solving, right? We're solving for y. Bring over the 1. And then, so I'll write like this. Y cubed is equal to, and then it ends up being the fifth root of x, and then minus 1. So I brought it over and swapped the whole function together. My root's a little large there. So subtract the 1, and then you just flip the equation. So minus 1. Okay, now what? Yes, again, you take the third root on both sides. So y is equal to the third root of all that. So it's the third root of the fifth root of x minus 1. And then set y equal to f inverse. So then f inverse of x is equal to all of that, which is the third root of the fifth root of x minus 1. No idea what that looks like. I just picked a question that was going to be a little more interesting. So when you're doing fifth roots and odd powers, then you don't have to worry about being 1 to 1. I mean, it is 1 to 1, because you don't have to worry about positive and negative when you do the roots. That's why I picked it. Let's look at some graphs of this stuff. So this is, so if you have a graph, and I'm going to copy this one as well over here. If I have it. Oh, wait, where'd it go? Let's go to here. Okay. So we're going to copy this guy. These look, because these are nice already. So let's look at these. Bring this one over. Oops. Bring this one over. I have it looking real nice for you. Let's copy that. And then the other one I can trace real easily. Just put that here. Style. Did I mention these are really unformatted and uncut lecture notes? I do so many of these, I have to. It's just they're time consuming. So let's look at this. Suppose you have the line y equals x like this, and you have this function f. So f is here. So f looks like this. And it goes through -1, 3, 3, 5, and 5, 8. So here's my function f. What we know is that f and f inverse, those two functions are symmetric or reflected. So I'll say are reflected about the line y equals x. So you see how there's a mirror image of that? So it's not like you're copying it over. It's like taking this page here and then folding it, and you're going to get this image. Notice that the domain and range are interchanged. So the domain and range are interchanged. So basically, x and y are interchanged. And see how that happened? This is -1, 3. It becomes 3, -1. 3, 5 becomes 5, 3. 5, 8 becomes 8, 5. So they're flipped. So it goes across the line y equals x when you do the inverses. So like when you're doing just a quick prelude to the future, if you're doing a how to hate it doesn't do my lines. Anyway, you're doing trig functions, and you have a sine function like that. Well, only a portion of sine is 1 to 1, and then now you're going to flip it basically around the line y equals x. So it's going to look like this. That's your inverse trig function. That's what you'll end up doing, and so you'll know the graph of an inverse just by knowing the graph of the original function. That's where we're heading with this. That's why it's important, not just for fun. Okay. Another example I did down there that you would have seen on the other page is what I mean, is if you just take the line y equals x again and you use, excuse me, let's make sure I get this right. Okay, there it is. That worked. So this is your line y equals x. And so if you're looking at the square root function, or x squared, so x squared will look something like that. So the reflection is a root x, a root function, and that's going to be like this. And so 1, 1, and it doesn't, see how that came back on itself? It doesn't do that. So make sure it doesn't come back on itself. It keeps going up. So let's see if I can get that to, yeah. So that's kind of what it's going to look like. But it's going to, I'm going to delete that. It's going to go through 1, 1 right here, whatever 1, 1 is, because that's the same value. That's on the line y equals x. That makes sense. Okay, so there's your root function. That's y equals root x. And this was your y equals x squared. Okay. Let's look at, this is the last thing in this section, and it's the theorem for derivatives of inverses. And we'll do one example of that. Okay. So here's the theorem. If f is 1 to 1, or is a 1 to 1 function, differentiable and g equals f inverse, and f prime of g of x is non-zero, can't divide by 0, then g is differentiable and, so basically its inverse is differentiable, and dx of f inverse of x is equal to g prime of x, that's just notation reminding you, equal to 1 over f prime of g of x, which really is 1 over f prime of f inverse of x. So you find its inverse and plug it in and then take its derivative of the original function. So it's kind of weird actually how that works, but that's how it works. All right, so, and I'm not going to do a proof of that or anything. We're just going to roll with it. It's not crazy important, but worth looking at. Example, we're going to do number 42 on page 377. So if you're really, into this right now, try it. Look it up and try it in the book. If not, well, just follow along. Okay, so we're going to let f of x equal, and this is just a polynomial, x squared minus 4x quadratic, I guess, minus 5. X is greater than 2. So we're restricting the domain to greater than 2. And that's probably because we want to have one-to-one function, of course. Find ddx of f inverse of x. So find its inverse. Okay, at x equals 0. And so f of 5. Why do I know f of 5? This is given. F of 5 is equal to 0. So that is 5, 0. Okay, so that would have been given. All right, so f, actually worked it out. F of 5 is 25 minus 4 times 5 minus 5 equal to, and that's 25 minus 20 minus 5 is equal to 0. Okay, so just to verify that. I think that was given. Anyway, yeah, I think it was. So let's do the derivative. So this lets us know, so at 0, so we know the inverse value. That's the key. So you don't actually, in this, the way we're doing this, have to actually find the inverse. That's what's kind of cool about it. So we've got to find f prime, though. So f prime of x is equal to 2x minus 4. Okay, and then I did a little diagram here to show you what's kind of going on. So you have f going like this. Five is over here, 0 is over here, and so this is the inverse going back. So f of 5 is equal to 0 implies then that f inverse of 0 is equal to 5. So when you evaluate and put 5 in for your inverse, that's what you get. So the theorem says d dx of f inverse of x, and it's non-zero and all that stuff. So hypothesis is satisfied, not being too critical right now, is 2x minus 4, but we're evaluating for the inverse. So that's what we're going to put 5 there, right? Because what we're evaluating for, I don't like that color. That's better. Is 5. So 5 is going here because we're going to evaluate at 0. So what is the inverse of the value? So we're going to put 5 right there. And so you get, so you evaluate x equals 5. And so you get 1 over 2 times 5 minus 4. 1 over 10 minus 4 is 1/6. So that's the kind of how you can evaluate it. That's what they meant by that. It can be a little weird at first when you're evaluating it because of the, actually have to find its inverse. So notice that we didn't find the inverse. We just evaluated the function and went back to figure out what the inverse value would be, which makes it kind of neat, actually, I think. Okay, that's it. Next one is 7.2. We're going to define the natural logarithm. It is really, really cool what we're going to do next. I'm really excited.